Hello, I'm Chantal Balkowski. I am an astronomer at the Paris Observatory. Today I'm going to talk about light. I would like to discuss the restrictions astronomers face due to the fact that their objects of study are not accessible, being simply too far away and beyond reach. The only information available is the light emitted by the objects. Over the centuries, astronomers sought to understand the nature of light, how to collect it, analyze it, record it, and finally, how to work the data obtained. Nature shows us the way. White sunlight is decomposed by water droplets, forming a rainbow. This is perhaps what inspired Newton in 1670. He experimented with a beam of white light passing through a glass prism. He observed the decomposition of the light, obtaining a spectrum on his wall. He proposes that light is made up of particles. In 1676, Roemer, at the Paris Observatory, determines the speed of light from his observations of Jupiter's moons. In 1690, Huygens proposes that light is composed of a series of waves that propagate through the ether. So, in the 17th century, we have two proposals for the nature of light. In the 19th century, physics is developing, and in 1801, Young does an experiment making light pass through two slits. He observes that behind the slits, an interference pattern occurs, which means light is a wave, because only waves can add and subtract to create a pattern of dark and light. The year 1864 is an important turning point as Maxwell combines electrical and magnetic phenomena in one single theory. He theorizes that light is an electromagnetic wave that propagates with constant speed. The electromagnetic wave is the combination of an electric and magnetic field that propagates in the same direction. We define light as a wave, with a wavelength defined as the speed of light divided by the frequency. Wavelength has a unit of length. The frequency is in hertz. The distance between two maxima is the wavelength. The speed of light is currently known to be 299,792 kilometers per second. But light is not the only electromagnetic wave. All the waves we detect are electromagnetic waves, and they make up the electromagnetic spectrum. The electromagnetic spectrum goes from the gamma rays with very short wavelengths through X-rays, ultraviolet radiation. You can see that the visible light is only a very small part of the whole spectrum, followed by the infrared and finally radio waves. The task of the astronomer is to construct instruments that allow to detect these different wavelengths. The only difference between these waves is the wavelength. They are all oscillating electric and magnetic fields. In the 19th century, Fraunhofer observes dark lines in the continuum spectrum of the Sun. He is unable to identify the lines except for some elements. Many other astronomers focus their attention on the solar spectrum. In 1850, Kirchhoff and Bunsen perform experiments with white light passing through a slit to obtain a thin beam of light. The beam is guided through a prism, resulting in a continuum spectrum, as we saw before. When the source of white light is replaced by a hot gas with low density, emission lines are observed instead of a continuum spectrum. Other gases give other emission lines. So, we see that the first characteristic of spectral lines is to allow an identification of the gas. Spectral lines are the gas's fingerprint. It is how a gas identifies itself. When a hot gas is cooled and illuminated by a white light source, dark lines are observed.
À la sortie du spectrographe, ce sont des raies sombres.
Scientists have derived laws to explain the formation of emission and absorption lines.
Les raies d'émission et les raies d'absorption sont fabriquées.
At about the same time, arises once again the question whether light is a wave or a particle. In 1900, Max Planck publishes his law of black-body radiation. This law states that the intensity emitted by a body at a certain temperature is a function of wavelength. These different curves correspond to bodies with different temperatures. The highest curve corresponds to the highest temperature, 7,000 Kelvin, and this lower curve corresponds to 4,000 Kelvin. You can see that the maximum for a hot body is at blue wavelengths, here in the visible part of the spectrum. On the other hand, the colder bodies have an emission peak in the red, and are thus colored red. At the same time, people questioned the photoelectric effect. It was not understood how a metal could eject electrons from its surface. In 1905, Einstein describes light as energy quanta, as already had been suggested by Planck, and proposes that the photoelectric effect is due to photons of infalling light. Each photon, having a certain energy, can extract electrons from the metal. Therefore, light must be made up of photons, each one behaving like a wave. Each photon has an energy, capital E, that is proportional to the frequency. The higher the frequency, the higher the energy. H is the Planck constant that defines this relationship. Because frequency equals the speed of light divided by wavelength, and we know that when the frequency goes up, so does the energy is inversely proportional to the wavelength. A large wavelength corresponds to a low energy. But there is more to the story of spectral emission and absorption lines. The question regarding the structure of matter is still unsolved at the beginning of the 20th century. In 1913, Bohr proposes a structure for the hydrogen atom, now called the Bohr model. In this model, the nucleus is composed of a proton and a neutron with one electron in a shell, or level, at a certain distance from the nucleus. Bohr shows that the electron can jump from level 1 to level 2, 3, 4, or 5, but these levels are not at random distances. The levels are quantified. In order for the electron at level 1 to jump to the second level, it must acquire the exact energy difference between the two levels. For example, here we observe the Balmer series. It corresponds to the electron cascading from different higher levels down to level number 2. To finish, I would like to show the link between light, wave, particles, energy and matter. Here is the summary of the principle of emission and absorption. An electron that is at a certain level receives a certain amount of energy to jump to the next level. This amount of energy corresponds to the exact energy difference between the levels and comes in the form of a photon. So, in Kirchhoff's experiment, this results in an absorption line. The atom absorbs the photon that arrives. However, the excited electron in the second level is not in a stable state. It will eventually fall back to the first level and re-emit the energy it had received, which is exactly equal to the difference between the energy levels, as I said before. So, it is the electrons at different levels with very specific energies that lead to the formation of spectral lines, in emission or in absorption. We now have the main tools of the astronomer, that is, how to measure the temperature of a body and its composition, how to determine the abundances of the chemical elements present and their relative importance to each other, and also how a body rotates and how it moves away. We will now look at what spectroscopy can give us vis-à-vis these parameters. First of all, why should we observe at different wavelengths? In fact, there are different types of objects that emit at different wavelengths. For example, compact objects in collision emit gamma rays. Here is an artist's rendering of such an object. Gamma rays, I recall, have short wavelengths and thus very high energies. Most stars that we observe emit in the visible. In the infrared, we observe dusty bodies. In the radio domain, we can observe quasars. Here in the center, you can see a quasar, a bright object that shows radio emission in the form of lobes, as we have called them, ejected by a jet. So, as you can see, different phenomena have maximum emissions at different wavelengths. We can also observe the same object at different wavelengths. Here you have an image of our galaxy from gamma rays to long radio waves. If you compare, you see that the galactic center shows powerful gamma ray emissions. It has lots of dust seen in the visible, including in the outer layers. We see it even better at infrared wavelengths. Note that each image is different. Finally, the hydrogen atom. You can see that gaseous hydrogen extends quite far away from the disk, much more so than as seen in the visible. So, observing at different wavelengths shows us different aspects of the same object. This allows for a better understanding of these objects, that being the goal of the astronomer, to understand how these objects work and what is the physics behind them. Let us see an example with stars. Stars emit radiation as a function of their temperature. From the spectrum, we can determine the star's color, meaning its temperature, and from the spectral lines, its composition. In the middle of the 20th century, stars were classified into different types, taking into account the presence of different spectral lines as a function of their temperatures. This is related to the theory of stellar evolution, which helps us to understand the evolution of a star as a function of its mass, how it is born, evolves, and dies.
En tous les cas, comment elles, selon leur masse, elles diffèrent.
Let us now look at how we use a spectrum to measure velocities. Here is an observation of the 21 centimeter neutral hydrogen line from a galaxy.
Qui caractérise l'hydrogène neutre dans une galaxie.
It has a profile with two peaks indicating that one side of the galaxy is approaching and the other side is receding.
Un côté de la galaxie s'approche de nous, tandis que l'autre côté s'éloigne de nous, et que dans le centre
In the center, we have fairly little hydrogen compared to the amount observed in the spiral arms and the disk of the galaxy, which is rotating like this. Similarly, we can measure the rotation curve of a galaxy by looking along the disk from the center towards the outer regions. We observe that the rotation velocity of the galaxy increases toward the outer regions, reaching a certain maximum value, whereas at the other side this value decreases. This is the signature of the rotation of a galaxy. Let us now look at the shift of spectral lines. The Doppler effect is well known. Everyone has experienced it when hearing an ambulance, a train, or another moving source of sound. When it approaches, the pitch of the sound is higher, and when it recedes, it is lower. The object emits sound waves with a certain frequency. Note that even though a sound wave is different from an electromagnetic wave, the Doppler effect works in a similar way. Therefore, even though we observe waves with different wavelengths, the wave is always emitted with the same wavelength at the source. The same happens in galaxies, called the Doppler-Fizeau effect, after Fizeau, who showed it to be the same effect also for waves of different nature, such as electromagnetic waves. The Doppler shift equals the difference in wavelength between the emitted wavelength and the observed wavelength, divided by the emitted wavelength. This ratio equals the speed of the object divided by the speed of light. Here you can see an historical image referring to the discovery of the redshift. At the arrow here, there are two absorption lines. When looking at a more distant object, these same absorption lines are shifted by the length of this horizontal arrow. An object even further away shows an even larger shift. I will show you how this effect was considered by Hubble. He measured spectra from a number of galaxies, such as M31, the Andromeda galaxy. This is the closest galaxy to our own, and it shows typical absorption lines for galaxies. On a different galaxy, he observed that the spectrum was shifted towards the red. You can see here that all the absorption lines are shifted towards the red in the same way. Here, the black and red curves. It is this shift that allows us to determine the velocity of the galaxy relative to us. In 1929, Hubble had access to a 2.5-meter telescope, the largest instrument at the time. He showed that the velocity of a galaxy equals the Hubble constant, capital H, multiplied by the distance to the galaxy. How did he arrive at this result? He measured the speed of the objects from the Doppler shifts seen in their spectra. He then independently measured the distance to the objects, all nearby galaxies, using variable stars called Cepheids. What he found was a linear relationship for these galaxies, showing that the higher the speed, the larger the distance. Hubble was thus able to demonstrate that the universe is expanding, a finding that would shape cosmology as we know it today. This is a scheme that is often used. It represents a balloon on which galaxies are drawn. As the balloon inflates, the galaxies separate from each other at a higher rate as they are further away from each other. This is the law of the expansion of the universe. So what is now needed are instruments to measure a large number of spectra simultaneously. This is achieved by using multi-slit or multi-fiber spectrographs, currently mounted on telescopes. It is not enough to observe just one object. Instead, we need to measure the spectra of hundreds or thousands of objects simultaneously. This is VIMOS, a multi-slit spectrograph mounted on the VLT. Here you can see how masks are made, and here are thousands of galaxy spectra captured onto a CCD camera. Let us look a bit more in detail how astronomers do this. First, they have to image the object, in this case a globular cluster. The small white lines indicate the objects chosen to observe. A mask is made by a machine which opens slits in a piece of metal. This mask is installed in the spectrograph in such a way that only spectra of the chosen objects are captured. The astronomer then takes a slice along one of the spectra, represented by the horizontal lines, thus obtaining a spectrum of the star or galaxy observed. There are also fiber spectrographs installed at the VLT. We have the giraffe spectrograph, which can operate in two modes. In one mode, it observes 135 objects simultaneously by positioning different fibers at the exact spots. The other mode is the integral field spectroscopy mode. Here, small sets of fibers are placed on a galaxy and a spectrum is measured for every square drawn here. The speed of the galaxy is determined at each point, enabling us to reconstruct a velocity field. This information is important to help understand the formation and evolution of galaxies at different redshifts. Finally, let us take a quick look at how astronomers have collected waves and light over the centuries. Galileo, 1609, the refractor.
très vite limité par
It is very
la
limited due to
taille
the
des
size of the
lentilles,
lenses.
puisque la lumière est réfractée. Donc, très rapidement,
Not much later, Newton proposes a telescope with a mirror inside instead of a refracting lens. Telescopes start to grow in size. 1788, 1.2 meter. 1847, 1.8 meter. Then, a 5-meter telescope at Mount Palomar in the 1950s. At the start of the new century, the 4 8-meter telescopes at ESO in Chile, the 2 10-meter Keck telescopes, and probably in the near future, the ELT, a telescope that will be constructed by ESO with 42 to 30 meters, expected for 2018. This project is still being debated. It is a long-term project, expensive and difficult to coordinate. A few words about radio telescopes used to observe radio waves. We can perform interferometric observations. For example, for the group of Messier 81, a small group of 4 nearby galaxies. We can see the advantages of the radio in comparison with the optical, or the advantages of combining both wavelengths. In the radio, we detect hydrogen gas emission, where in the optical nothing is seen. This allows us to understand the interaction between these galaxies. Observations done from space have several advantages. There is no atmospheric turbulence, as opposed to observations done from the ground. Here is the center of our galaxy, a very rich region observed in the infrared. Note that when using an Earth-based system that allows to correct for the atmospheric turbulence blurring the image, we can separate the stars. In the non-corrected image, we observe rather blurred areas, and it is not possible to separate the stars. In space, there is no atmosphere, so this problem does not exist, which is an advantage. Another important advantage is that from space, we can observe radiation that cannot be detected on Earth. This is fortunate because gamma rays, X-rays, and UV are rather energetic, so it is a good thing that we have the atmosphere to protect us. It also means that we need to construct satellites equipped with telescopes able to observe at these wavelengths. Unfortunately, their mirrors are smaller in size than on Earth, and repair is not possible once the satellite is launched, with the only one exception of the Hubble Space Telescope. The missions have a limited lifetime, mainly because they have helium on board to cool the electronics, and helium has a limited lifetime. In general, a mission does not last more than 2, 3, or 4 years. The Hubble Space Telescope, with a 2.4-meter mirror, observes in the visible and the infrared. It has obtained the deepest images ever of some regions in the sky. The XMM telescope is able to observe X-rays. Here we see very hot gas found in the center of clusters of galaxies. The different colors represent the intensity of the gas. There is much more hot gas in the center of the cluster, and the more outer structures have been interpreted as gas falling back onto the central mass. All these images taken in different wavelengths, either from the ground or from space, are used to make composite images. This infrared telescope has observed Messier 82, a very irregular galaxy. The red areas show dust observed by this satellite. The blue colors represent X-ray emission observed by another satellite, and the visible image from the HST is shown in orange and green.
ici résumer tous les conséquences
Therefore,
et
this image summarizes everything.
résumé de tout ce que
All
l'astronome peut
wavelengths
faire
an
en
astronomer may
fonction des questions
observe,
qu'il se pose.
depending on what he
Et
looks
les
for and the
questions
science
physiques
questions he
qu'il
wants to
faut
address.
résoudre, eh bien, il observe avec l'un ou l'autre télescope. Les télescopes du futur, eh bien,
Telescopes of the future.
les télescopes de
On the ground,
sont
40-meter telescopes are being designed and sizes are being
taille
defined.
encore bien définie et qui pourrait être vue à la baisse. Par contre, le
In
télescope,
space, the future
dans
James
l'espace,
Webb Telescope will have a diameter
le
of
James Webb
6.5
aura un
meters.
diamètre de 6,6 mètres. Dans le domaine radio,
In the radio
maintenant,
domain,
au
on the
sol,
ground,
un
there is an important
projet très
project
important
for which
dont
international
les accords
collaborations have just been agreed
internationaux
to,
viennent juste d'être signés,
named
le projet
SKA, the Square Kilometer Array.
Donc, il s'agit
It
d'un
is an ensemble of radio
radiotélescopes
dishes
et de
and
tuiles
aperture
qui
arrays
observeront,
that will observe about 1 million galaxies,
jusqu'à
thus
1
pushing
million
forwards
de
radio
galaxies
astronomy in a
dans le
dramatic
ciel.
way.
Donc, des progrès attendus dans le domaine de la radio très importants.
These projects have a horizon beyond
C'est
2020,
en marche.
but are being prepared as of now.
Et peut-être un jour des réseaux de satellites.
And perhaps one day we will have satellites flying in formation and doing interferometry in space, which may well detect life on planets around other stars.
Des traces de vie sur des planètes extrasolaires.
I thank you.